Hi, welcome back to my channel. Today we're going to talk about the calculus of wealth. Have you ever wondered why people say that compounding interest snowballs? Or why we try to keep our management cost of index or the cost of the management of my stock as low as possible, or whatever financial products we want to keep that low. Okay, so this can be actually explained through mathematics as well. So today we're going to look at how the exponential power of compounding creates this snowball effect that we have always talked about. So let's first understand what is a simple interest and what is a compound interest. So in the simple interest, the growth of your interest is fixed on its base. So I put in 10,000 at the start of the year. 10 years later, I am still going to calculate my interest based on $10,000. Although my interest may be 3% per year, but your interest doesn't earn you more interest. For compound interest, the growth builds on your growth. That means your interest earns more interest. Okay, and then why does it snowball and how fast does it snowball? We will look at it. So let's look at the anatomy of simple interest and compound interest. So in simple interest, the future value is equals to PV times 1 plus RT. So for those of us who learn mathematics and knows something about linear functions, we can see that this is of the form y equals to mx plus c, right? Which is a linear line. On the other hand, for compound interest, future value equals to present value times 1 plus r to the power of t. This is exponential, right? So this is exponential. So in real life, usually, okay, the bank will tell you the simple interest is say 5%, while the compound interest is 3%. Okay, if I were to have the same rate of interest for both simple and compound interest, both are 3% or both are 5%, definitely we will choose the compound interest. But in reality, some simple interest rate will be higher than the compound interest rate, and there's a reason for it, because even if I give you a lower compound interest rate, after a certain time, okay, I will always have a break-even point, okay, which allows the compound interest to earn more than the simple interest. But this, of course, happens very, very long time later. Okay, so as you can see in this graph, if I have simple interest 5 and compound interest 5, it takes very long for it to break even. Okay, so let's look at some calculations first. For compound interest, okay, the 10-year growth comparison of $1,000 at 5% for simple interest and compound interest. So you can see every year you only earn $50 interest from the compound interest, right? So you add on 50, 50, 50, 50. At the end of 10 year, you only have 1,005. But for compound interest, because your interest earns more interest, you can see that every year, the interest that I earn is a little more than the previous, right? So if I calculate the difference between these two, and so on, you will see that I have increasing interest earned year on year. And you will be able to see that, okay, your money is working harder for you in year number 10 than it was in year number 4, although you didn't put in any extra money, because the interest is that extra money that actually helps you to build this growth. And you can see the difference is actually quite big, right? So let's look at why this is true. Okay, so to look at the growth of a function, we actually look at how fast the gradient changes. So the gradient, okay, of a curve is defined as the change in y values, okay, per unit increase in the x values. So usually we have y equals to a function of x, and then I'm going to look at how the gradient changes. I can use simple mathematics like rise over run, or y2 minus y1 divided by x2 minus x1. But to be more rigorous, we will actually look at the gradient function, which is dy dx equals to f prime x, because this is called the gradient function of any curve, of any function. Okay, can be linear, can be constant, can be exponential, or whatever. So let's look at what happens. So I have, in this case, okay, I said that the r is equals to 1 plus r power t. This is our compounding formula. So I'm going to look at dr dt. Over here, I have two things, r and t. R is going to be a constant because I assume that, say, my compound interest rate is the same throughout 10 years, 15 years, 20 years. Okay, I'm just going to give it a fixed number r. So t is my only variable. So I can do dr dt. Now, this is an exponential function. So when I differentiate it, it is 1 plus r power t multiplied by ln 1 plus r. So the differentiation rule that we use is d dx of a power x equals to a power x ln x. Right? So now let's try and see what this tells us. Okay? This tells us that the rate of change of my capital R value depends on two things. This exponential, 1 plus r power t, and multiplied to a factor, a constant factor. What factor is that? It is ln of 1 plus r. Now, when r is a fixed value of, say, r 5% or 10%, ln 1 plus 0.05 or ln 1 plus 0.1 is a constant. So I know that I am growing, okay? But I'm growing at an exponential rate as well. That's why we have the snowballing effect. Because compound interest compounds based on the interest rate exponentially, right? So I have a constant number multiplied to the exponential function. The whole growth becomes exponential, and that's where your compounding happens. Okay, so if we were to put things into context, you will be able to see my r equals to 1 plus r power t. I found my dr dt. If I set my r to be 0.05 and I work out my d capital R dt, you can see that year 1, okay, is smaller than year 2, and then it's going to be smaller than year 3, and so on, so on, so on. Until year 10, you can see that the growth is very fast, right? That's why I am able to have this snowball effect. And I have actually proved it mathematically. So I start out with a very gentle curve. And as time goes, because of my compounding effect, my gradient becomes steeper, which means that my interest earned increases with time. And I get a steeper gradient as time goes. Hence, the compounding effect has a snowballing effect as well. Now that we have seen what is the snowballing effect in compounding interest, let us look at the rate sensitivity of a compound interest. Now, why do we want to look at rate sensitivity? Because this will actually determine, okay, whether we invest or we buy certain financial product based on its expense ratio or the management costs and things like that. Because you will see that as much as how compound interest compounds, that drop in investment returns rates will also cause us to lose some money over the years. So you can see that if I have a compound interest of $1,000 at 5% versus 6% annually. Okay, the first year my difference is $10, but the second year, because my interest earns interest, my 6% growth will have a little bit more interest than my 5%. Hence, now it becomes 21.0. And then the third year and so on, because the 6% always generate a little bit more interest than the 5%, the difference in that interest also grows. So you can see by the 10th year that 1% difference initially costs you to have a difference in $161.96. So overall, okay, what is the difference in my returns? It is actually the whole sum here, which is a lot, right? Now let us look at why we have the rate sensitivity to be true. So again, I start with capital R equals to 1 plus R power T. Previously, T is our variable of interest because I'm comparing what happens when the time changes. Okay, now we are trying to find out what is the rate of change of my capital R when I change my rate of return, which is my small r. So now the variable of interest is small r. And with that, we will see that T is a constant, 1 plus R is a variable. We are actually going to use the differentiation rule for polynomials, which says that differentiate x power n equals to n x power n minus 1. So my d capital R over d small r becomes T times 1 plus R power T minus 1 multiplied by the differential of 1 plus R, which now gives me just this. So with this, I know that my rate of change of my gradient with rate of return, which is my small r as variable, is also a polynomial. So what will happen is that when R has a small change, okay, when there is a small change in R, we call it delta R. Okay, my delta capital R equals to dr times delta R, which tells us that T times 1 plus R power T minus 1 multiplied by delta R will be my change in capital R. So you can see when I do a little increment, okay, of that delta R, my rate at which delta R is changing follows polynomial. So my delta capital R change as a constant multiplied to a polynomial function. So you can see at T equals to 1, the returns increase by 1%, but at T equals to 10, the returns increase by a staggering 15.5%. So this tells us that when I invest long term, my returns becomes hypersensitive to the rate. Okay, a change in the 0.05% every single year. Okay, the difference between two products, okay, is 0.5% return is hypersensitive to the rate because you're compounding snowball, remember? So a 1% rate increase at year 10 drives a 15.5% increase in returns. So I do not want that to be rock in my investment, right? So this mathematical rule, of course, works in reverse as well. If my rates drop by 1%, okay, your returns will plummet by 15.5% also. So that means if I invest long term and my nominal rate of return drops because of a market not doing well or whatever, okay, you also need to be aware that your returns of course will be affected, and that effect will be 15.5%. So we have looked at rate sensitivity and we have looked at the snowballing effect. So now it comes to the 3 golden rules. Okay, I want to make sure the product that I have been investing in optimizes for fees. So losing 1 to 2% in fees devastates overall returns by a lot. So if my management fee is higher, I would want to choose the one with lower management fees if the returns are similar for 2 products. So the math that showed this is actually the rate sensitivity dr over d small r. I also want to maximize my time in the market because we have seen that your money working at the first year, okay, is less hardworking than the money that is working at the 10th year. So we have showed this in the snowball effect, which is d capital R over dt. So the last golden rule is that your portfolio size amplifies impact. When your portfolio is small, microscopic rate changes matters less. But for large portfolios like in the 500,000 or 600,000 or 1 million, a tiny rate change has a massive absolute impact. So this is the combination of both the snowballing effect as well as rate sensitivity. So a lot of us may think, I start with a small portfolio, I just choose anything that I want, I don't care about all the rates difference and returns and so on. But when you are serious about investing and you put in money for a long term, you need to start thinking since the day one that you have been investing. Thanks for watching.